Okay, so let's start. Welcome everybody. Today's a pleasure for me to introduce Professor Attila Geresdi. Attila is an experimentalist. He's an expert on low temperature transport and low temperature nanoelectronics in general, microwave experiments, hybrid semiconductor, superconductor systems, and this kind of stuff. He graduated he did his PhD in Budapest University of Technology and Economy in 2000. He graduated in 2011. Then he moved to Delft, to TU Delft in the Netherlands, where he was a postdoc in Leo Kavenoffen's group for 3 years, I believe. Then in 2015, he got a Veni grant. And with this grant, he was able to start as an independent leader, still in Delft. And then he got a senior researcher position, where he got a few important grants, I have to say, like an ERC grant. And also he started to lead a FET Open project on Andreev levels in hybrid semiconductor, superconductor systems. This is the topic actually of his talk today. And since a bit more than a year or so, he moved to Sweden, to Chalmers University, where he already has started a lab. He has, I think the lab is almost ready, I believe. And he has his own group there. And he's producing very, amazing experiments. We will see some examples during the talk today. So again, it's a real pleasure for me to introduce Attila, and I'm looking forward to this talk. So please, Attila, when you want, you can start. Thank you.
Thank you, Ramon, for the kind introduction. So let me just do the share screening, and I just the entire screen, and I will put this into presentation mode, and I believe now it should work for everybody. But as the most important question is in physics is whether you see my slides, I have to ask the same now.
Yeah, it's good. Go ahead.
Okay, so thank you very much, and also for the nice introduction, Ramon. And it is my pleasure to be here virtually with you today. And indeed, as you mentioned, I will talk about mostly the results and vision of our Andreev qubit project that's run together with several partners throughout Europe, and also with external collaborators outside of Europe, actually. And before starting with the physics, let me acknowledge my coworkers at Chalmers, which is my current group at the Chalmers University of Technology, as well as my prior coworkers at TU Delft. We are also having a long-term collaboration with the Center of Quantum Devices in Copenhagen, both for materials exchange as well as theory collaboration by a group of Jesper Nygaard and Jens Paska, respectively, as well as the same in at the Yale University in the United States, with a group of Leonid Glasman for theory collaboration and experimental collaboration with a group of Michel Devoret. And also, we are happy to collaborate with the group of András Pályi at the Budapest University of Technology, also for their theoretical modeling of some of our devices. And indeed, what I will talk about is Andreev bound states and how to actually look at this physics and how to exploit this for quantum technologies. One thing that I forgot to mention is that I'm happy to take questions throughout the talk, but I'm not sure how we can technically do that. Probably the best is if the organizers kick me if someone tries to ask me a question, and then I will try to answer the best as I can. So let's get started. So before going to the actual physical system that we are working on, it's actually good to have a recap of superconductivity, which is typically described by this density of states where we have the excitation gap of single quasiparticles and the Cooper pair condensate in the middle. And of course, since this is a bosonic condensate, this can be described by a global wave function, which has an amplitude which is sort of proportional to the square root of the Cooper pair density, and there is a global phase just like for any complex wave function. And this global phase is actually meaningless unless you actually couple two superconductors together. And the simplest way to do that is to actually do that with a thin insulating layer where first order Cooper pair tunneling is, so weak coupling is possible between the two superconductors. And in that case, what was shown by Brian Josephson and later measurements confirmed this, is that a dissipation-less supercurrent can flow, which has an amplitude which is called a critical current, and it has a sinusoidal phase dependence on the phase difference between the two superconducting leads. And this is actually an important achievement because that's subsequently led to a lot of superconducting devices, so in particular superconducting quantum bits, where this global condensate is actually used either for either the charge part or the phase part of it. I'm not going to go into the details, but the point is that this teeny tiny object, the Josephson junction, is actually now the base of a lot of quantum technologies that are in the forefront of both industrial and academical developments. But of course, there's also another side of the story that the reason why this is actually a good avenue towards quantum technologies is because the Josephson junction is inherently boring. Because I mean, it's very simple to describe it. It has a sinusoidal current phase relationship, and pretty much that's all there is. So that it doesn't have its own life, at least at the energy scales, as far as the Cooper pair tunneling is concerned. So then this is actually good for scalable quantum technologies, but it immediately makes us asking the question whether we can do other weak links between two superconducting leads. And the answer, luckily enough, is that, of course, yes, we can. And what I'm going to talk about is what happens if we put a semiconductor nano device, in this case, a semiconductor nanowire elongated nanostructure between two superconducting leads. And here, this is a prototype object of this nature where we have the superconducting banks on the left-hand side and the right-hand side of this device, respectively. And we have a region where we don't have the bulk superconductor, but we have this semiconductor weak link that we can just gate electrostatically, just like if it was a field effect transistor. In this particular device, this is actually built off this nice material science development that was done in the Center of Quantum Devices around 2015, where they showed that certain semiconductors, in particular, this is indium arsenide, here 3,5 semiconductors, and some superconducting materials, this is aluminum here, which is also frequently used in Josephson junction-based technologies, can be epitextually grown on top of each other. And then indeed, as they were shown in these publications, both the materials and actually the quantum transport shows quite nice and almost perfect features. So then here you can see that it's an atomically perfect interface between the two materials, and also it exhibits favorable properties for superconducting technologies. So in particular, what we show here, and this is similar to what has been shown by the group of Leo Kavenhoven actually quite earlier, is that these kind of devices can be operated as a sort of a Josephson field effect transistor, where the transition between the superconducting branch, where the device has no resistance, and the finite resistance regime, and the transition between them is called the switching current, can actually be tuned by the gate voltage. And this is sensible if you think about it, because what you tune with the gate voltage in a normal device is the charge carrier density in the weak link region. And the charge carrier density can also determine how much Cooper pair current we can actually pass through this device. So then, apart from some fluctuations here, the general behavior in these type of devices, at least in these indium arsenide devices, is that if you increase the gate voltage, then you induce more electrons into the weak link region, and then consequently you also increase the switching current as a function of the gate voltage. So this is a Josephson field effect transistor, and if you just think about this, then we can actually already do a lot of things with this type of hybrid devices, and I'll just showcase a few here, and I will only talk about some parts of them in the interest of time. So then perhaps the most important motivation recently for these sort of devices was that it can be used as a means of inducing topological superconductivity in these hybrid devices if the semiconductor material parameters and an external magnetic field and the induced superconducting gap together are in the right regime, that this can lead to Majorana-bound states in the boundary of topological and non-topological superconductor. I believe Pada has talked about this earlier, so then I'm not going to cover this in detail. One can also do different things. For instance, one can do multi-terminal Josephson junctions out of these devices. So depending on how these nano devices were grown, crosses or even more complex structures can be grown here. If you think about maybe more simple devices, one can just make a transmon qubit, but without a Josephson junction, with actually a nanowire as the weak link between the two pads of the transmon, and then there is a gate tunable transmon, commonly referred to as a gate-mon in the literature. And this can, for instance, have the advantage that compared to a normal tunable superconducting transmon, this is not flux sensitive to its Josephson energy, so then it can be resilient to that noise source, but of course it can pick up other noise sources if the gate is in particular noisy. Nevertheless, this has been demonstrated by a group of Leo Di Carlo and also a group of Charlie Marcus in Delft and Copenhagen, respectively. And one can also make more complex weak links. So then actually the weak links, we can also make some its own life. And what we actually demonstrated more recently is that we can measure supercurrent via a double quantum dot device and then see how the charge and spin states interact inside the double quantum dot with the Josephson supercurrent that we pass through. I will also talk about this. But if we actually think about the physics of these weak links, then what we have to introduce is the Andreev bound states. And these are single electron/hole states, respectively, that leave localized to this weak link between the two bulk superconducting banks. And the reason why these are localized is that we can think about this as a particle in a box problem, just like in quantum mechanics courses. But the only difference is that the boundary condition for this particle in the box is actually depends on the phase difference between the two superconducting banks, because now we have that as a part of a degree of freedom. And of course, since this has to be a localized state, that this has to be below the superconducting gap in the leads on each side. So then this can actually be solved. This problem can be solved in certain limits. In particular, the most famous one probably is the short junction limit, where this weak link is much shorter than the phase coherence length in the superconductor. And in that case, there is this simple closed formula that describes the energy dispersion of these Andreev bound states in this weak link. And then, as you can see, basically it describes those properties that I mentioned earlier, that it's bounded by the bulk superconducting gap, and it has a dispersion as a function of the phase difference, because the boundary condition for this particle in the box, it depends on the phase difference between the two sides. So this is this is how the Andreev bound states enter the picture. And another property that it's good to make a connection to is the supercurrent dispersion. As I mentioned in the beginning, the supercurrent for a Josephson junction, which is a tunnel junction weak link between two superconducting banks, has a sinusoidal current phase relationship. So that means that the supercurrent has a sinusoidal dependence on the phase difference. But if you think about, if you look at this dispersion, which is non-sinusoidal, so non-harmonic on its own, it has higher overtones, then of course also the supercurrent will have higher overtones. So then this actually inherently describes higher order Cooper pair tunneling processes. And for instance, in this weak link limit, it can be described by this equation. So then this is simply the phase derivative of the previous Andreev bound state expression that I showed you, and this is clearly non-sinusoidal. However, if we go back to the original limit, which means that we take this tau, the coupling between the two sides, the tunneling probability between two sides, very small, then we actually get back the Josephson relation. So then that's then we have a supercurrent which is sinusoidal and is proportional to the superconducting gap and this tunneling probability between the two sides. And the good thing is that this can actually be measured. So then, for instance, we have this type of geometry, which is a DC squid. for this purpose that we fabricated, and then my PhD student at TU Delft demonstrated in his PhD thesis in 2017, is that if we have a DC squid like this, where we have a larger weak link, which is now a superconducting tunnel junction in a classical sense, and then we have this nanowire weak link which can be gate tuned, and then this is this entire object can be flux biased by means of an external magnetic field, which is applied perpendicular to the substrate. Then we can actually work out the phase drop on each of these junctions. And then one particular limit is that if this larger weak link is much larger than the weaker one that we want to characterize, then by the critical current of this entire DC squid, we can actually work back the current phase relationship of the smaller weak link. And the way this works is that at the critical current of this entire object, the total phase drop has to be pi/2, because then that's where you have the maximum supercurrent for a sinusoidal weak link. And that means that what we will have as an oscillating critical current of this entire squid will be the critical current of the larger junction, and it will be modulated by the the current phase relationship of the smaller junction shifted by pi/2. So this is the theory. Let's see how it works. So this is an experiment performed on this class of device, and then indeed what we find is basically what I described earlier, is that we have the switching current of the large junction, and then we have a small modulation on top of that, which is attributed to the nanowire junction here in this case. And then indeed this is clearly, I would say, almost triangular, so then strongly non-sinusoidal, which indeed motivates our picture of having highly transmittive modes in these semiconductor nanowire devices. So that's actually a good thing, but of course it's even more interesting if we have some structure in the weak link, and the most simplest maybe structured weak link has been measured again in Delft quite some time ago in 2006, and then this was the geometry that they used for this purpose. So then you can see the same squid geometry that I described earlier, and here you see one weak link which can host a quantum dot inside, and then there is another weak link which is much stronger than the first one, but it's just a single transparent channel. So then if I want to translate it to a schematic, then it would be something like this. And then what they measured with this geometry is the same thing, the modulation of the critical current of this entire squid, which then describes the current phase relationship of the quantum dot that they put inside. And of course, the theoretical modeling is now a bit more convoluted of this device, because if you think about a quantum dot, in particular with the large charging energy limit, then certain virtual processes will have to transfer these two electrons that form a Cooper pair via this quantum dot in order to form a supercurrent. So then you have to take these two arrows from here to here, and there are certain rules for that. And this can be made via virtual states. And basically the important key take-home message is that if there is no electron to begin with on the quantum dot, then these Cooper pairs can be electrons that form the Cooper pair can be transferred one by one. And that means that we can just get, again, in first order, sinusoidal current phase relationship. But then if we actually go back to single electron occupation already on the quantum dot when we start this process, then we actually have to flip over this Cooper pair, and that means that this will result in a negative critical current 0 to pi transition, supercurrent reversal. And this actually has been shown on multiple devices. So for instance, the first measurement was done here in this indium arsenide nanovirus, showed this device here. And then indeed, depending on the charge state, so now this is this VL electrostatic gate that tunes the charge state of the quantum dot, and you can see that on neighboring charge states, you indeed have a 0 to pi and then back to 0 phase difference between the critical currents or the switching currents of this device. So then on the horizontal axis, you have the gate voltage, and on the vertical axis, you have the applied flux on this DC squid. Indeed, it picks up a 180-degree phase difference. Now, if we think about other devices, so then this has also been shown on carbon nanotubes by multiple groups, as well as on indium antimony nanowires subsequently. Basically, pretty much always the same outcome, that if you go with the, you take the current phase relationship as a function of the applied flux, then there is always a 180-degree phase shift between neighboring charge states. But of course, this is actually much more interesting if we think about double quantum dots. But of course, it's also more convoluted in the technical sense. So then if we look at a double quantum dot device, then of course, first of all, what we have to realize is that we even have much more device parameters than what we had for a single quantum dot. And then we have this characteristic honeycomb structure of the stable charge states on a double quantum dot device that that show you what kind of stable charge state you have, stable charge number you have on one left quantum dot and on right quantum dot as a function of the one gate and the other gate that you can apply on this device. And what is even more interesting is that one can also take a look at the spin states of this double quantum dot device, and in particular in the single occupancy region, there is a on the double occupancy 1-1 region, one can actually have a singlet to triplet transition as a function of the magnetic field, because at zero magnetic field, the singlet and the triplet states split up, and the singlet wins in energy, but then the triplet down eventually gains energy enough as a function of magnetic field because of the Zeeman field, so then it will take over. So then it's reasonable to believe that if we put this device in a Josephson junction, then or in a squid, and then we measure the current phase relationship over it, then the spin states will influence the processes, the virtual processes that will determine the supercurrent on this entire device. So we set out to measure this, and then here you see the device that my PhD student Daniel Baumann put together, and then here this is the same type of indium arsenide nanowire, which is a epitaxial aluminum shell, where the aluminum shell was edged away in the middle, where this double quantum dot was formed by 5 wraparound gates, out of which 3 gates can tune the coupling between the leads and between the quantum dots respectively. And there are 2 plunger gates that tune the charge states on each individual quantum dot. And then the DC characterization can actually indeed show you nice honeycomb structures, as well as we can characterize the charging energy and the tunnel coupling between the quantum dots. Of course, and now if we turn on superconductivity, which means that we turn off the magnetic field that has driven the superconducting leads to normal, and first what we see is that indeed we can distinguish between neighboring charge states, and so then singlet and doublet states by the means of the YSR states that show up in between them. And then what we can also once again characterize is the superconducting gap that's relevant for these processes, which is 130 microelectron volt. So this we can do with finite voltage by spectroscopy. But now what is more interesting is that now once again we can put this back into a DC squid, where we have one single nanowire that form both of the weak links, and then the structured weak link is this one, and the non-structured weak link, which is the stronger one, is this one. And then what we want to observe once again is the modulation of the entire switching current with the small proportion, the double quantum dot critical current on top of the big one. So this is what we actually observe. So then we basically, for all of these experiments, we remove the background, and then the only thing that remains is the double quantum dot switching current. And then indeed in this experiment, and now this is purely switching current spectroscopy, indeed we observe the same honeycomb structure as a function of the 2 side gates that tune the charge states. And then indeed we see a supercurrent reversal between the neighboring charge states. And this can also be described by theory a little bit more in detail, just like more in detail than what I described it. And then indeed one can make a correspondence between the effective charge states of these double quantum dot by means of this correlation with theory. But what is even more interesting is that we can also do this as a function of magnetic field. And then the way we are going to do this is we take a line cut here across these 2 charge boundaries that we cross here. So then here we have a negative supercurrent to begin with, and then here we have a weak positive one, and then here we have the total charge boundaries between the 2 states. And we can take this line cut as a function of the magnetic field, and what we try to observe is this singlet to triplet transition. So then this is what we find here. So then here we have the horizontal axis, which is now characterized as the left quantum dot charge state, but of course it's always this entire line cut here. And then we can observe the switching current of the double quantum dot as a function of the magnetic field. And what we find here is actually this intriguing behavior that if you now indeed take this charge state as just a single spin occupying the two quantum dots, and here we have the two electrons occupying the double quantum dots, so in 1-1 charge state, then what we actually find is this intriguing behavior that first, once we increase the magnetic field, the charge boundary between the two sides as measured by the supercurrent, once again, it moves to the right, and above a certain point, it actually starts to move to the left. And this is actually consistent with our picture of singlet to triplet transition on the double occupancy region, because if you think about it, then near zero magnetic field below the singlet to triplet transition, which is this finite magnetic field. On the left-hand side, we have a single spin, which actually gains energy by Z1, by the Z1 energy as a function of the magnetic field. So it gains space compared to the singlet, which is effectively spinless. But once we pass the singlet to triplet transition, now we are actually dealing with two spins on the double occupancy side. So then now this side will gain more energy as a function of magnetic field. So it will actually turn back from going to the right to going to the left. And then we can also do this more in detail if you take into account the exact spin orbit coupling and the Zeeman energy. So then this is our experimental data with the error bars around it, and this is the theoretical modeling. Also, with the same parameters, we can also describe the supercurrent amplitude as a function of the magnetic field in the singlet to triplet transition. And what we also find here is that corresponding to the magnetic field where we have this crossover, we actually have a reduction of the supercurrent. And this is also consistent with theory which describes the triplet blockade of the supercurrent, which is not there when we have a singlet state in the double quantum. And so what we learn is actually the G factor of this double quantum dot, if we assume that there is one single G factor that describes the entire thing, as well as the spin orbit coupling parameters, which are meaningful for indium arsenide nanowires. So this is great because now we have actually a device that that can indeed couple this singlet to triplet transition to the supercurrent. So once again, we only used supercurrent spectroscopy here. But now, for the sake of the rest of the talk, let me just go back to the Andreev levels and talk about other weaklings, and then we can summarize our what we learned later at the end of this talk. So if we go back to the Andreev levels, again, now go back to the short junction limit. Then if we want to actually directly observe the Andreev levels, not via the current phase relationship of the supercurrent, then one way that was developed by the Sackley-Contreras group is actually to create excitations from we can take a look at this in two pictures, either the semiconductor picture of superconductivity or the excitation picture, where we have the excitation from the lowest occupied state to the higher state. Or in the excitation picture, we can also take a look at this as a breaking up of Cooper pair and then put the two resulting quasiparticles on the Andreev bound state that's above it. But basically the point is that regardless of what picture we take, the physical outcome is the same, that for resonant excitation, we actually have to take a photon energy, which is twice this Andreev bound state energy, so then the 2 delta times this expression that depends on the transmission probability and the phase difference between the two sides. And of course, the only difficulty with this experiment is that it actually requires some broadband spectroscopy of the photon energies that we can put in. And luckily enough, we can actually do this with superconductivity once again. And the way we can do this is we can couple another superconducting tunnel junction to this nanowire junction. And the reason why we can do this is the process called inelastic Cooper pair tunneling, which means that if we have a superconducting tunnel junction and then we displace the two Cooper pair condensates with respect to each other, then we can only take this process, meaning that we can only have a supercurrent between DC current between the two sides, actually, if the photon energy matches the energy difference between the two sides of the Cooper pair condensate energy difference between the two sides. So that means that we have a tunable microwave source with a rather convenient translation, roughly 500 megahertz per microvolt applied voltage bias on this superconducting tunnel junction. And then the DC current will actually be proportional to the dissipation that this photon sees in the environment. And then there is this simple equation, which is really just the conversion from microwave energy to the DC Joule heating in the environment. So then from the microwave photon energy, which is proportional to the critical current square divided by 2 times the real part of the impedance in the environment, which will peak in resonant excitations, is the same as the DC current times voltage that we measure on this superconducting tunnel junction. So this has been measured on multiple physical systems. The first measurement that I found was performed in the Saclay Quantronics group in 1994, where they measured what happens if they enclose a superconducting tunnel junction of this nature in basically a microwave harmonic cavity. And indeed, what they found in the DC IV characteristics of this superconducting tunnel junction is equidistant peaks, which is then indeed corresponds to our picture of equidistant energy excitations of a harmonic oscillator. Of course, now what we want to do is different systems. So we don't want to excite a harmonic oscillator, but we want to excite the Andreev level. So then our resonant condition will be different. So then it will be the Andreev level energy as a function of the phase difference of our nanowire junction will have to match the voltage and hence the photon energy of this microwave spectrometer. So the way this actually works in real life is shown in this device that we fabricated in Delft, where we have the spectrometer superconducting tunnel junction on one side. We have the measured nanowire junction on the other side, which is enclosed in this squid. So then it can be phase biased. And because we want to do basically microwave to DC down conversion, we have to put AC coupling between the two sides. So then these are these big coupling capacitors between the nanowire side and the spectrometer device side. And once again, on the spectrometer, we will create microwave photons and we will measure the back response of the nanowire junction physics. And this is what we hope to pick up. So let's see how it works in real life. So then this is an actual experimental data from this device and published in this paper, where we have on the horizontal axis, the applied phase bias on the nanowire junction. And on the vertical axis, we have the spectrometer voltage in voltage, but it can also be translated to microwave photon frequency if one is so inclined. And then indeed, we have these dispersing lines as a function of the phase which correspond to the Andreev physics inside this nanowire. Of course, the reality is always a bit more complicated than our simple picture. So then in fact, in these experiments, we invariably have multiple lines. So then we always have the Andreev lines as well as we have the plasma lines which correspond to actually this extra Josephson junction that we have in this squid. And then we observe both. So then the plasma line should be weakly dispersing and then the Andreev line should be strongly dispersing as a function of the phase bias that we apply. And then we can, from this simple picture, we can also actually extract the characteristic superconducting gap that corresponds to these Andreev states as well as the channel transmission. What we can also do now, since we have a gate tunable weak link, we can actually change the gate voltage, hence the charge carrier density inside the nanowire. And then from mesoscopic physics, we know that this should lead to opening multiple transmitting modes. And indeed, this is what we also observe in the Andreev bound state physics. So then at low gate voltages, meaning low charge carrier density, first we only see only one line dispersing, and it fluctuates a lot back and forth. So it's not really a clean system at that point. And then we have at some point a second one coming in and the third one, fourth one, and so on. As we increase the charge carrier density, we see multiple propagating modes and hence multiple Andreev bound states. And at high carrier densities, we can also take a line cut as a function of the phase, and then we see the individual Andreev bound states as a function of the phase, each of them corresponding to one propagating mode. What is also an interesting question is what can we do as a function of magnetic field with this Andreev bound state, because it's a spinful system. And this can be this can actually be done by considering the pair excitation, the spinful pair excitations as they propagate from the ground state to this split up Andreev bound state as a function of the phase difference. What we see here is, of course, always the total photon energy, so the sum of these two energy levels. And then this can be actually described by a simple model that corresponds to a G factor of roughly 15, and again, a spin orbit coupling energy, which is reasonable for indium Marzian. So then this theory has been done by Bernard van Hecken and published in his paper, and then we also showed in our experimental paper. Okay, so then this is the basics of Andreev bound states, and then of course the question is, can this be quantum? Because now we have to sort of propagate to the quantum technologies part, and of course the answer is yes, it can. Of course, we have to have some little bit more considerations of how microwave excitation and what kind of coherent processes we can have in these systems. And then what we have to actually consider is the different parity sectors of Andreev bound states, which is then we have an even parity sector and then we have an odd parity sector. And in the even parity sector, we either have no excitation on the Andreev level, or we have a pair excitation, which is a broken up Cooper pair. Both electrons going to the Andreev level. In the odd parity sector, however, we can have single quasi-particle charges on the Andreev bound state, and then those can also be spinful. And of course, in between these two parity sectors, the way we can go is actually parity switches, which are ubiquitous in superconducting nanocircuits. In other words, quasi-particle poisoning. So then, in order to describe this, basically, this is our simple schematics that we have to consider. So then we have the Andreev bound state where we have a phase bias applied by a superconducting loop. And then we always enclose this with some harmonic oscillator. This can be either another Josephson junction if this is in a DC discrete, like in the previous experiment, but it can also be a microwave resonator, like for circuit QED readout purposes. But invariably, there is always a characteristic impedance that can either be worked out by the Josephson junction parameters or the characteristic inductance or capacitance of the resonator. And this means that this part of the circuit will cause phase fluctuations on the Andreev level, which are proportional to the square root of the characteristic impedance, meaning that if we want to have strong coupling, then we have to increase the characteristic impedance of the resonator. And now we can actually go full Hamiltonian on this. So then we have the resonator Hamiltonian, which is the harmonic oscillator, and then we have the Andreev bound state, which now as an argument actually has this phase fluctuation here. And since I'm a simple physicist, the only thing that I can do is do a Taylor expansion of this thing. So then now we have the harmonic oscillator, the Andreev bound state at the prescribed phase bias, plus this coupling term between the two sides. And this coupling term, which is proportional to the phase derivative of the Andreev Hamiltonian, will actually couple the 2 degrees of freedoms together. So in particular, the simple case to show is actually when we apply phase bias of pi. So if you remember from the Andreev bound state picture, then this is where the Andreev bound state energies are the lowest. So it's a convenient operating point anyway. And then now we can actually work it out in a rotating wave approximation, this Hamiltonian. And then basically what this yields to is that there is a characteristic coupling energy between the 2 degrees of freedom, which is proportional to the superconducting gap, this characteristic impedance, and the transmission of the Andreev bound state, which will then in turn cause a dispersive shift in the dispersive limit, which is proportional to the square of this coupling energy and inversely proportional with the detuning between the resonator and the Andreev energy level. So basically this forms the basis of how these Andreev bound states can be operated in a circuit QED geometry. And indeed, so then if we have now this dispersive shift, then with this dispersive shift, we can actually distinguish between basically these 3 states that I described earlier. So then we either have a ground state of this Andreev level where we only have where we don't have an excitation on the excited state, or we have the odd state where we have a single electron on the excited state, or we have the even excited state where we have both electrons on the excited state. So let's see how this works in practice. So then now what I'm going to talk about once again is this even parity sector and how this can be operated. And this is an experiment that we have fabricated the samples for, and then it was performed in the group of Michel Devoret at Yale. So then here we have a superconducting resonator. This particular geometry I will talk about later. And here we have the squid in which we enclose the nanowire junction, and then the Andreev bound states can be tuned by this electrostatic gate, this purple object that comes in from the left-hand side of the circuit. And if we zoom out, then we see that this can be phase biased by an applied external magnetic field, which is perpendicular to the substrate. And then this resonator can be then read out by conventional circuit QED technologies. And then indeed, what was observed in this experiment is basically confirms our simple picture, but it actually has quite some nice fine details into it. So then this is a time domain experiment of the state assignment of this Andreev bound state with the phase dispersion of the frequency dispersion of the resonator. So then what we find is indeed essentially 3 states that we can distinguish between, and this correspond to the 3 states that I described earlier. So then we have the ground state, the odd excited state, and the even excited state, and also the characteristic energy, characteristic time scales for the switches between these states actually have some nice details into it. So then, as you can see, the ground state and the even excited state actually switches back quite a lot. But then once it switches to the odd state, then it's quiet for a long period of time. And then once it switches back, then it again jumps back and forth quite a lot, and then it's quiet, and then so on and so forth. So this clearly describes for us that there are actually 2 time scales at hand here. One is the slow dynamics, which corresponds to the parity lifetime of the system. So then the time scale of quasi-particle poisoning. So then in this case, this was extracted to be 160 microseconds, and subsequent experiments sort of yielded the same time scale, so the same order of magnitude. And then there is also this fast time scale, which can be seen as the qubit lifetime, the T1 lifetime of this object, which is actually much shorter. And in this particular experiment, it was 3.2 microseconds. So then now we have the basics of how to build these Andreev level states into circuit QED systems. So now it's actually timely to ask the question, okay, can we build, for instance, multi-qubit systems out of these devices? And what we have to consider is actually a tricky situation, because we have quite some different physics than what is normally considered for typically used transmon qubits, where you have a transmon qubit, which is basically a big capacitor coupled to this coupled to a circuit QED geometry. That means that it's electrostatically it's coupled by the electric field, the dipole moment, to the resonator. But if we look at the Andreev qubit, it actually has a different coupling Hamiltonian, so it's actually coupled by the current operator instead of the charge, the dipole moment. So consequently, we actually have to put this in a different physical location inside circuit QED geometry. And then now if I can just give you a very simple overview of how this works. So then this is a typical planar superconducting resonator that one uses for state assignment and readout of a qubit. This is how typically it looks like. This is actually was fabricated on a transparent substrate. So that's why here you have white, and then the blue parts are where it is covered by a superconductor. So this is called a coplanar waveguide. And then this is basically a pipe organ, if you will. So meaning that the length of this resonator will decide what kind of resonant frequency it will have. And most importantly, it will also decide in which part there is going to be the maximum oscillation of the current or the electric field. And for a transmon, you have to put it into region where you have the maximum oscillation of the electric field. But here, because of this coupling operator, for an Andreev qubit, we actually have to put this into a physical location along the resonator where it has the maximum oscillating current. And so that means that we, including the electrostatic tuning of this semiconductor structures, we actually will have to cut off the return electric current of this superconducting resonator where it has the highest current density. And that's actually a problem. So then we actually have to go away from this conventionally used coplanar waveguide geometry. And then what we have to work with, and this was already shown in the first experiments, is we have to go with a different geometry. It's called the coplanar strip line. But the good news is that afterwards we actually make this switch, then it will become scalable. So now you see a completely different geometry where you have this differentially driven sort of U-shaped superconducting line, and all the yellow parts of this circle is actually just empty substrate. So there are no superconductor, planar superconducting thin film there. And now the way this was actually done in this first experiment is that you have a similar device here. So this is this coplanar strip-line resonator. And here at the highest current density, which is just at the end, the non-excited end of the strip-line resonator, you couple the qubit to. And then this is now convenient because here you can actually put the electrostatic gating for the semiconductor nano device as much as you want, and then there are no restrictions imposed by the ground plane requirement of the coplanar waveguide resonator. And of course, this also means that now this is actually scalable in the sense that we can even put multiple qubits along the same resonator. So then if we have a current antinode here and another current antinode here, then we can actually have some resonator mediated coupling between these two Andreev qubits. And this is actually something that we are now working on. So, and in view of the time, maybe it's actually a good idea if I now conclude. So then I actually discussed 3 different topics throughout this talk. The first one was the even-odd supercurrent reversal of a double quantum dot device, and what I demonstrated to you supercurrent switching current measurement is that the singlet triplet transition actually does suppress the supercurrent that can flow through this device, meaning that this is an interesting avenue to go with spin to supercurrent direct conversion in semiconductor nano devices. In the next part of the talk, I was talking about Andreev bound states in single nanovariate Josephson junctions, so no quantum dots in this case, but just single transparent weak links, and I showed how these Andreev bound states can actually be detected in the broadband microwave spectroscopy geometry. And finally, I was talking about a circuit QED readout and circuit QED geometry for single qubit and multi-qubit Andreev level systems. And with this, I hope I'm still in time, and I would like to thank you for your attention, and I'm happy to take questions.
Thank you very much, Attila, for the amazing talk. So now it's time for questions. So you can raise your hand, and I will let you unmute yourself and ask the question, or you can write it in the chat, whatever you prefer. So is there any question? Maybe, let me see. So maybe I can start, Attila. The question is about the last part where you advance the possibility of having multi-qubit systems and couple them together and using this new geometry. The question is how dangerous is a quasi-particle poisoning, in the sense that now you have, once you have multiple qubits, you have many degrees of freedom that you have to control, and you want to stay always in the appropriate Hilbert space of your qubit. Is this something different from the single qubit, or is it more or less the same problem, or what do you know about this?
Yeah, it is indeed a good question, but yeah, so stray quasi-particles is a good question in general for superconducting devices. So then what I would say is that the reason why we can be hopeful that this is going to work is that apparently the quasi-particle lifetimes of these devices actually at least, I don't know, 1 or 2 orders of magnitude higher than any other timescales of these quantum devices. So then even if it goes wrong with say larger scale devices, we hopefully still have enough headroom to investigate this further. But indeed, what would be the best is to mitigate quasi-particle poisoning, and I don't have a direct idea on this. Maybe one could actually think about clever feedback schemes to actually always push back the device to the right quasi-particle parity regime real time. I mean, such feedbacks can be done if it's doesn't concern very fast timescales of quasi-particle poisoning. So, for instance, can be an avenue to look into.
Okay, thank you. There is a question by Ruben Seoane. I think you can unmute yourself, Ruben, and even switch on your camera if you want. Okay, good.
Yeah, thank you. Thank you for the nice presentation, Attila. I was wondering also about the odd parity state. Is it always detrimental for applications, or can you use it for your advantages? Say, for example, you want to find a qubit and you say the 0 state is the even parity state and the 1 state is encoded in the odd parity state. Is it possible?
I mean, okay, so the thing is that then you go out from your coherent subspace, so then you basically cannot operate it as a qubit by super selection. But what you can do is, and there is actually this publication from last year, also by Yale group from our collaboration, is that what one can do is actually look into the spin state in the odd state and then use that as a qubit degree of freedom. And that can indeed be done, and that's actually has different timescales and different physical limiting factors and sort of pair excitations of the Andreev level qubit. So for instance, I can imagine, and it looks like it's more sensitive to the spin bath, nuclear spin bath inside the nanowire, but maybe it's less sensitive to other, say, gate charge noise or other noise sources. So this is actually still being actively investigated. But the short answer is that yes, the odd state can also be used as a qubit degree of freedom, and then you have to stay within the odd state, and then we have to basically use the quasi-particle spin degree of freedom to basically define a qubit degree of freedom.
Thank you.
Okay, good. So now there is a question by Elsa Prada. You can unmute yourself, Elsa.
Very well. So, Attila, thank you very much for this wonderful talk. I really enjoyed it a lot, and then I'll watch it again afterwards to really follow all the details, because there are indeed many useful details. Well, I have a question about the double quantum dot critical current results. And is that looking at the shape of this critical current, I find it is very similar to what happens with topological wires when you go from the trivial to the topological regime. Can you comment on that? Why would be that so?
So which feature are you referring to? Maybe that's...
So that the critical current decreases as you
as a function of magnetic field. Okay. I mean, okay, so in this case,
in a very similar fashion.
Yeah, indeed. So that is a good point. I'm not sure if it's the same physical reason, but here we actually have two things that point towards this singlet to triplet transition, and then the corresponding supercurrent decrease is not only this amplitude decrease, but also the shape of the charge states. Basically the shape of the charge boundary as a function of the magnetic field. So here you have this internal degree of freedom, which corresponds to basically the charge parity of the double quantum dot charge state, and the shape of that also changes as a function of magnetic field. So, and this is how we sort of put these Lego pieces together to form this entire nice picture.
Yeah, so how
for a topological wire, I don't think that you have this internal degree of freedom. So then. Yeah, then I would believe that then the physical picture is different.
But you also go from a singlet superconductivity to this P wave, which you are losing one of these.
I mean, the leads themselves always stay singlet.
Okay, I see.
So then it's merely the assigned spin state of the double quantum dot that changes.
Okay. I see.
So I wouldn't call this triplet superconductivity, because the banks themselves do stay singlet. It's basically the same aluminum lead with high enough critical magnetic field so that it can actually survive this interrogation.
Okay, very well. And a very quick question. So to really have a qubit at the end, let's say of the road, there are several requirements that we always look for. No, these requirements that need to be satisfied. And my question is, in your opinion, what would be the best candidate, Transmon qubits or Andreev qubits? If I had to,
I would say that at this point, I mean, the honest answer is that no one knows what is going to be the best scalable qubit.
Mm-hmm.
So basically, this field is so much open. Of course, I mean, with transmon qubits, there is a big headway that has been done by the industrial players in the field. Mm-hmm. But I mean, it's still way below what one would consider actually a useful quantum computer. So I would say that at this point, no one really knows. Maybe Andreev qubits will be more scalable on the longer run, but this is actually just the beginning of this field. So then we still have to look into it, and then we have to do our best science to actually get the best physics, and then hopefully that will be the best technology as well.
Okay, thank you very much. Bye.
So there is now a question by Denis Crete from TNRS. You can unmute yourself, Denis, if you want.
Yes, thank you. Thank you very much for this wonderful presentation. I was wondering how would you do to observe Rabi oscillation, or has it already been done?
Yes, it has been done both for the even excitation and the odd excitation. So it's published in these two papers.
Okay.
Rabi oscillations and also echo experiments to actually get the coherence times out of these devices.
Great.
And then the short, basically the take-home message is that the echo time for the pair excitation, I think it was roughly 500 nanoseconds for this experiment, and the T2 time for the spin excitation was actually more like order of 10 nanoseconds. So then there is still clearly some points of improvements there.
Okay, thank you very much.
And now there is a question, or a couple of questions by Sole Vaitikenas. Hi, Sole. You can ask your questions.
Hello. Hi, Attila. Thanks for the nice talk. I was wondering if you thought more about how the circuit QED signatures would change in a parallel magnetic field. I guess you talked a little bit about it in the middle section of the talk, but from this even odd and ground state picture. So yeah, basically I was wondering how it would change, and if you thought about it, can you elaborate a little bit more on that? So that was question number one.
Yeah, so actually the interesting thing is that in this, at least if you have a multi-channel system, then to have a spin split up in the odd state, you actually don't need an in-plane magnetic field. So then if you break the symmetry by a suitable flux bias, then you can already have a spin splitting.
Is it similar to what they did in Hayes' Nature Physics paper?
Yeah, exactly. That's exactly that.
But okay, good.
And then the point is, sorry, yeah, please go on.
So I was just wondering, in single channel limit, if you spin split that,
okay, so
does it get very complicated?
Okay. So in the single channel limit, if I recall it correctly, then the symmetry conditions are such that you basically cannot operate. You don't have a spin splitting in the odd state, at least zero magnetic field for sure. And I think that the problem is that if you have a short junction single channel, then at least in that limit you cannot have, you don't have a matrix element between the two spin states if you have a spin split under a bound state. So consequently, in first order, you basically cannot drive the transition.
Got it. That's what I thought so too, but I couldn't find a lot on that.
And then basically you have to go away from that condition. So then what was shown in the Sacre quantum group is that if you have a multi-channel device, then it's already sufficient to actually drive these transitions. Okay.
All right. And then I had a second question back to the first topic that you were discussing on the different weak links in a Jocelyn junction, and you showed that you can have supercurrent reversal, so basically a pi shift. I was wondering if you thought more about engineering different phase shifts and maybe even higher harmonics by using different weak links, and if it's even possible.
Yeah, so okay, so then I think that there are then two questions here. One is that whether you can make an arbitrary phase shift. And the answer is that in finite magnetic fields you can, and then we indeed observed that. But it was not part of this study because it's actually yet another complication for basically on different physical grounds. And the other question is whether you can have non-sinusoidal current phase relationship, and in principle you can, but the problem is that even the first order, well, not first order, lowest order coupling by a double quantum dot is, if I recall it correctly, is a 6th order tunneling process. So then anything higher than that actually would require a double quantum dot in a very strongly coupled regime. So I would say then both observing well-defined charge states, and that would be difficult at the same time.
Got it. All right. Thank you very much.
We actually did confirm that in this experiment. I didn't show the data, but we have it online, if I'm not mistaken. Is that for this data that we have in this paper, the CPR itself is sinusoidal.
Got it. Thank you very much.
To good experimental accuracy. So.
Thanks.
Okay, thank you, Shole. Now there is a question by Edu Lee. Please, you can unmute yourself, Edu.
Hi, Attila. Thank you very much for the nice talk. I was wondering also about this double quantum dot experiment. It seems that, yes, with respect to the expression of supercurrent as a function of magnetic field, it seems also for your doublet state, you also see your overall for the gate range study, you see overall suppression of the supercurrent. And can you comment a bit on this? And
sorry, can you repeat it, because maybe I was.
Yeah, the sound is a bit difficult. Edu.
Sorry. No, I was mentioning to the double quantum dot experiment, where you have the measurement as a function of gate voltage and magnetic field, and where you see the suppression of the supercurrent that you attribute to singlet triplet. It seems to me that overall you see a drop in the supercurrent for the entire gate voltage range, also for the triplet, or sorry, for the doublet state. Could you comment a bit on this? I mean,
okay.
It's really
yeah. So then indeed, basically, okay. So then observing a drop in critical current or switching current as a function of magnetic field is a bit of a tricky thing, because you anyhow expect it even without any interesting physics. What we do see in this experiment is that indeed there is a global drop in the switching current as a function of magnetic field, but in the singlet/triplet side, it's actually a faster cutoff than in the doublet side. So the only thing that we can comment here is that indeed the line shape is different, but of course it would be a stronger argument. And the other argument that I can make based on this experimental data is that we have this change in the charge boundary between the doublet and the singlet/triplet state, and then the two things correspond to each other. So that's why
in the line shape, you mean
that the kink of the
they don't occur at the same field, essentially, or you mean that the singlet to triplet it coincides with the singlet to triplet kink, but in the doublet side it doesn't. I mean, the drop doesn't occur at the same field.
Yeah, exactly. So then in the doublet side, the drop is just a slow drop as a function of magnetic field, but it's actually much, it becomes a much more step-like. It's still not really step-like, but more step-like in the singlet-triplet side.
I see.
And this drop corresponds to the singlet to triplet transition as we extract it from the charge boundary, the shape of the charge boundary.
I see.
So that's why we have this picture.
Okay. Yeah, got it. Thanks. Just one more thing about this, the left part where you talk about the Andreev level population. Perhaps I missed it, but as you show, you have quite a lot of dispersion in the Andreev levels with gate voltage, and that you have a lot of other Andreev levels entering. So at what regime do you actually operate this, and how does it influence really when other Andreev levels enter when you tune the gate voltage essentially?
You mean in the regime where we have multiple Andreev bound states because we have large enough charge carrier density, multiple channels. So the thing is that in the circuit QED experiments, we are actually quite limited in frequency range. So then it's essentially it's always, at least in these experiments, one Andreev bound state that one can capture, which is close to 0 at phase equals pi, close to 0 compared to the superconducting gap, so the total pair excitation, which is 90 gigahertz. So then that's why we don't really observe multiple Andreev bound states or don't play in this physics. The other reason for that is that in the circuit QED readout, your resonator can actually select very well from different degrees of freedom. So then that means that if your line shape is sharp enough, then you don't couple the two things together.
I see. Okay, thanks a lot.
Okay, thank you, Edu. So are there more questions? I don't see further questions. Let me see in the chat. No. Okay, so if not, we can thank Attila again for the nice talk, and thank you all for attending.
And thank you for inviting, and
we can clap.
Have a nice lunch at this time.